Hello everyone and welcome back to a new video in our Robot Structural Analysis Professional video series. In this video I am going to be talking about plates and some advanced stress results that you can obtain from Autodesk Robot, such as complex stress and principal stress. So with that being said and without further ado, sit back, relax and enjoy the show. Okay, now I'm gonna start by clicking New Project and selecting something called the Building Design, just because I want to have a template to start my project with. Now here, I'm gonna define me a very simple plate because the goal of today is to explain what the meaning of different stresses are and talk a little bit about the design of plates. So let me just add me here some X and Y positions. So I'll add me here, I don't know, like 0, 4, and 8 in the X. And though I'm going to add me a 0, 3, and 6. And in the Z, I'll just keep it as is. I'll apply and close. So now I have a grid. I'll go to View and look at the grid from 3D. Here, I will be defining a steel plate. So my floor now is going to be a fully fledged steel plate. I'll basically go to my thickness here. I will not find a steel plate, so I'll click here and ask it to make me a steel plate. If you're overwhelmed by this, double check the Robot Basics playlist I will be linking on the top right, as well as the basics of plates and shells I will be linking also on the top right. Here, I'm gonna make me a homogeneous steel plate. I will say here, I don't know, I need a name for it. Steel, I don't know how thick it should be. I'll just call for a 75mm thickness. Now, I'm not sure if 75 is good or not. I'll just add a 75mm and worry about those later. Now, I want to mention something about steel plates that is very important. If you plan to have a steel plate that covers a span, then you will be surprised how thin your steel plate might be acceptable in a code. However, a pitfall in those plates is that they vibrate. You don't only need to check if the plate is good in shear and moment and stress and axle and whatnot, you also have to check its vibration capabilities and how it would vibrate under transient foot loads. Anyway, for now, I just want to talk about the stresses. So I'm just putting nodes here. I selected geometry node and now I'm clicking on nodes here. I misclicked, Control Z. I'm clicking nodes here because I want to apply support to those. So now I'm just adding me some nodes. I'm adding nodes here because I want to add a support and I want to focus on support number 8 here. So I'm going to add me all pins. So I'll click here, add me pins. I don't know if I might need to add a fixed support for stability. I need to check that out. I'll click on load cases. I'll add me a dead load and a live load. There we go. In the dead load, I will add me, now there is self-weight included. If you go to loads load table, you will see that there is a self-weight already defined. I close the load table and go back to the structure. Now here in the loads, I need to select the dead load, of course. Here in the loads, I'll go to surface load. I'll add me, I don't know, a 0.5. Now you can see here Pascal, the units seem to be wacky. I think I messed up my units. So if you want to check units, click on Tools and then go to Job Preferences. In the forces, Newton. Okay, I want to have kilonewtons here. The reason why I have newtons here is because I was doing benchmarking for my software, Strado. Let me just go once again and save them as defaults. Yes. And now if I go back to the loads, I can see kilopascal, so kilonewton per meter square. I'll add me a load in the Z, -0.5, and I'll add that. Click here. Did it add? I don't see. Let me check. -0.5 in the Z. Okay, apply. I can't see it. Is it a bug? Okay, let me just double check again. Loads, load table. It seems it did not apply the load. It didn't, yes. That's a bug in Autodesk Robot. If you have something on base, you are unable to click it. So I'll go here, edit, move, and I'm gonna move it up. Now, this is a very strange bug that happens sometimes to me, that if you draw something on the brace level of a building, it doesn't click well. So now let's try again. Going to load definition, surface, there we go, add, and now we click, and there we go. Yes, it was a bug. It happened to me, I think, in my warehouse video series. I forgot. But if that happens to you, if you're unable to add loads, just this is a bug in Robot that in the base level it seems that clicking doesn't work. So now we have the load here. Fantastic. I go to live load now, and I'll add me a load. I'll add a surface load and add me a load. Now those loads are something I'm not really thinking about too much. I'm just here to show you the stresses. So I'll add me a load. This might be not a very realistic load, but that's not my point today. Now I'll go to my combinations. You go to loads, manual combination. I will do a manual one. It's a ULS. I'll add that and just apply those two things, apply and close. Now, before I start, let me preface this that Robot doesn't have a plate steel design module. So it's kind of ambiguous of how you would do the steel design. I've talked about this in the past, but here is my take on it. There are multiple possibilities to design the steel plate. You could just take a strip, meaning you could go to results and then click on panel cut and design strips. How do you define strips? Well, with panel cuts. Now let me show you the maps so that you know what kind of strips you need. If you go to results, maps, now you can show the, for example, moments in the XX and hit the apply button. And a quick reminder that the moment in XX is going to follow the local X direction of the plate. If you wanted to follow the global X direction, you can click on automatic direction and you can switch to Cartesian X global, but I don't want it, so I'll keep it on automatic. That's the first thing. Now notice something very peculiar. It seems that the moment is very high near the column, very higher near the middle column, and it's kind of low between the columns. In both directions, you see this behavior. Near the columns, they are high, away from the columns, they are low. Not only the moments, you can even see in the shear forces Q the same behavior. It seems that near the columns, the forces are more violent than when we are away from the columns. Now, this should not surprise you because you studied something called a column strip and a middle strip. So one way of doing an analysis and design of a steel deck is to not use von Mises and complex stresses, but just go like this, define yourself a cut, and define yourself a cut one time moving parallel to X, one time moving parallel to Y, and perform your checks. Allow me to show you. Now, I'm not going to do the checks for you, but I want to explain to you the principles of that, because Civil Engineering channel is all about principles. So now I will go and ask him to make a cut parallel to the Y, to the XZ, parallel to this plane. So let me just cut parallel to the XZ and click, let's say, this point. If you click this point and click apply, you get a panel cut, and you can see the results of the panel cut. Now they are zigzaggy because the mesh is kind of coarse. If you want to make a finer mesh, you can click here, click on job preferences, and go to work meshing, and just select, for example, normal if you want something that is a little bit bigger, smaller sized. If you run the analysis again, the results update and you get a smoother moment diagram, something that you can see here, and that's that. So that is a panel cut in X, but this is a column strip and a central column strip. In order to design the plate, you would have to design it in the maximum section. Now, you can immediately see that the maximum section is happening here, so that's the section you should be checking out for designing. Now, you could do other sections. If you want to add another panel cut, just click on New, and once again, select a point. Let me select, for example, I don't know, this point here, and I'll apply, and you get another panel cut. You can see the panel cut here. If you want details about the panel cut, you can go to something called diagrams and ask it to show you some labels and some filling, which is kind of cool. It shows to you the diagrams filled and labeled, which is cool and looking in 3D. And if you want to, for example, see the insides of a panel cut, you can go to cuts here, click the cut you want, and go to diagram analysis, and then you can see details of the cut with its full glory. You can even move your cursor and it will show you the values. I mean, if you click on in the point and then move your cursor, you get the values of the panel cut at each point. So you can use this to design your plate. And my suggestion here, because look, the AISC doesn't explicitly consider the von Mises stresses as a yield criterion. Von Mises stresses is a yield criterion for multi-dimensional stress. So you could just take 1 meter width strip and consider it like a beam and just do your calculations. It is not the cleanest version because you're missing a lot of things, but that's the version I can think of, because in the ISC code, you have a tension member, compression member, bending member for beams, but plates are seldomly talked about. If you know a code chapter that talks about this, please tell me in the comment section and I would gladly make a video about it. Of course, you can also add some cuts in the other direction by going to cuts. There we go. Let me first of all turn those off because I don't want to see them. Let's hide them. And now in the maps, because I want the other direction, it makes sense, for example, to choose MYY, the other direction. Let's say we don't want MYY. Let's say in the other direction we want to check shear. Let's mix it up. So I click on shear QYY. So now I'm showing shear in the YY direction. Now here, let me just go to cuts. Where is it? Definition. By the way, you can click back and forth here on the top if you want to check different tabs, or you just can hover here and you can see all the tabs. Now I'm gonna make me a new cut. This time I want to go this way, so it's YZ. I'll go parallel to YZ. It's passing through this point again, so I hit apply. And now you see this crazy diagram. Why do you see this crazy diagram? Because you need to check what the cut shows you. If you go to cut, make sure A33 is selected, and then when you go to detailed, it shows to you what the cut is showing. The cut at the moment is showing moment XX. However, the map is showing shear YY. It doesn't make sense. So let's let the cut show shear YY. And now suddenly everything makes sense. And this is the cut for the shear YY. You can add more cuts if you want. Go back to definition, click the new, select another point, for example, this point, hit the apply, and there you go. You have another cut. Once again, it's good to click on cuts, click your target clock, cut, go to details, check what it's showing, and indeed it's showing QYY. And now you know how to get the moments and shears for each cut, which is a 1 meter strip, and you can design that using the AISC code. So this is my suggestion to designing plates. However, I want to talk about something totally different. So I click on clear the view here to get everything back to its defaults, and let's talk a little bit about the stresses that are shown here. Complex stresses, and so on. So I'll go first of all to results and to maps, and let's talk a little bit about stresses. So if you click on stress XX and click apply, strangely, you see nothing. Zeros. You can see everything is a zero. Now this is very peculiar because, I mean, you have loads, right? You have loads, so obviously there must be stresses. However, the stresses seem to be zero. If you go to stress YY, they are still zero, which is even crazier. Like, how are there no stresses here? Well, the reason why there are no stresses is because the stress changes with the location among the section. And allow me to explain this very quickly. If you have a section like this, and you apply a pure moment to the section, then usually there will be tension on the bottom, compression in the top, and in the center exactly, you would have a neutral axis, meaning the stress here is zero. This is different if you have an axial compression force, because then you would have a stress that looks like this, small tension here, big compression here, and in the center, you have not a zero stress. So what I'm saying is, because your loads are causing pure moment, there will be no stress in the middle layer. If you look, the layer of stress is middle. And if you go to normal forces or membrane forces, you don't see any membrane forces. Now, allow me to show you some stress. If you click on loads and you just add yourself, I need to select a case. If you add yourself a surface load that is in the X or in the Y to kind of produce a normal force, if you just add like this, let me just click on it, there we go. So now I have a normal force. If you click on analyze now, suddenly you will see stresses in the middle layer, because you have in the neutral axis of bending, you still have stresses in the axial. Now that's not what we want to talk about. because we are not going to artificially create stresses in the middle layer. So I will delete the last load I added. I totally forgot which one it was. Okay, it's this one, the one with the X force. Let me just click here and here, and then push the delete button and basically get rid of the load to get back to my normal force here. Of course, I get gibberish here because I have to perform analysis again. So I run the analysis again to kind of normalize the scales a little bit, and now I get back to nothing in stresses. Fantastic. How can I show stresses in different layers? Well, it's actually very easy. If you go to parameters here, you can see what kind of place you want to have your stress in. For example, if you click upper and apply, now it shows the stresses in the upper fiber. And you can see that the stress is positive in the upper fiber near the reinforcement because you have a hogging moment, and the hogging moment causes tension on the top fiber. Of course, if you go to the lower fiber, then you get the compression here, because in the lower fiber, a hogging moment causes a compressive stress. So you can see where this is going. You can select upper for the stress at the upper fiber, topmost fiber, lower to the lowest fiber. If you click on maximum, usually for this Q bending, you might have a equalish position. You can just click on those things if you want. You can even select an arbitrary position at a certain position, but I will just leave it as is. I'm just gonna select now the upper. So now everything we talk about in terms of stresses is on the upper layer. Allow me to show you something very peculiar. You can even change the view to make it easier for you to find results. If you click on result and go to results maps, for example, then Robot switches itself up to be dealing with maps specifically. You can see even that the tools change, and you can, for example, here define panel cuts as you see fit. So you can see that this is kind of a dedicated view. I don't want to stay here because there is a chance that you might jump here and be overwhelmed by the shape of Robot. I click here and go back to structure model and geometry. Fantastic. So now for the question, what is principal stress and what is complex stress? Now, if you click on principal stress follow the stuff you study from Moore's circle. If you click on sigma 1, you get the highest sigma. And how does it do that for you? It takes an element, and I mean, you studied this in mechanics of materials. And if you, let me explain it to you. In the detailed, you have stresses in X, stresses in Y, and shear stresses. If you select principal, this is sigma 1, that's sigma 2, and that's tau for you. You can even verify it by clicking on help. If you click on help, just click here on help. Sometimes it helps you. Click something to show maps, and if you click here, it will open for you what those things mean. And you can see here some documentation, because I got a question from our dear subscriber, and you asked me about the documentation. You can easily access it here. Principle explains to you exactly what the theory behind this is, and it shows to you sigma 1, sigma 2, S12, and it tells you what those are and the angle of the principal stresses. Those are the angles where the principal stress is occurring. And in case you're wondering, why is the maximum shear stress 0? This is the shear stress perpendicular to the element. Yes, my bad. 1, 2 is the shear stress parallel to the element. Yeah, okay, fine. So you can see some details here. And if you ask what the theory behind this is, you can just click on formulae or formulas determining those stresses, and it will give you the formulas. This is actually the Moore's circle formula. Because the question was, how does it calculate this? This is the Moore's circle equations. That's what you studied in mechanics of materials. And this is what happens here. If you go to, and see, before I continue, I just want to reiterate the philosophy of CEE's channel. It's not just to dish out how to use the software. Because how to use the software, there are millions of silent YouTube videos. Just click, 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 and that's it. No, we are here to understand what happens behind the scenes in the software. And even I'm trying to learn how to learn. And that's our objective here. So this is the S1, S2, and so on. For the complex stresses, this is the von Mises hypothesis. Now, the von Mises stresses are based on the von Mises yield criterion. What is the idea of the von Mises yield criterion? You see, here is the explanation, but it's far deeper than what I will try to do. If you click on S von Mises, you get the stresses in the von Mises calculation. And the von Mises calculation is used as a yield criterion. Allow me to explain it to you. If you have a steel bar and you say this steel bar has a strength in yield of 420 megapascals. This is the one-dimensional yielding, meaning if you apply a stress in 1D 420, then it will yield. Now, this perfectly works for members of linear nature, like beams and columns and whatnot. But in a plate, you know that there is a combination of stresses in the x-axis, stresses in the y-axis, stresses in the 1-2 axis, which is the shear axis, and all kinds of stresses in a plate. So suddenly, the 420 is to be shared with the x stress, with the y stress, and with the shear stress. And nothing shows it more than Moore's circle. So is there a failure criterion to do so? And the answer is yes. It's called the von Mises yielding criterion, and it depends on the stress deviator from the hydrostatic axis of stress. Now you think I am making those things up. This is really high-level stuff. The thing I want to tell you, to try to simplify things, is that your yield criterion can be based on von Mises, and you will have to compare it with the yielding strength of your element. Okay? So you have von Mises here. You can even have Tresca as another criteria, and you need to make sure that your stress in von Mises is less than your yielding criteria. You can study this in a book. It is a book from De Souza Neto, and it's a very famous book explaining the von Mises stress in detail. So to wrap up, I've suggested to you a way of designing those plates. I've explained to you what principal stresses mean, and I've shown to you what complex stresses mean. I also explained to you the theory behind those things. I told you some further reading about von Mises stress, either from Wikipedia or from the book De Souza Neto, Computational Methods for Plasticity. It's an amazing book. I studied it in my PhD. I want to give a shout out to my dear Professor Udo Nackenhorst from the University of Hannover, who was my doctor father. And I was like dealing with this in my PhD. This might be a rather strange video. This is once again back to the principles of Autodesk Robot. I don't want you to just be a robot clicking and applying stuff on robot. You need also to understand what exactly is happening behind the scenes, what is the theory behind what you're doing. So I hope that this gave you further details about what principal stresses are and what complex stresses are. So with that being said, I hope that you enjoyed the video, and in the end, I want to give a von Mises stress-sized shout out to my team members in the contributor level and the helper level, whose names are going to be shown on the screen. I want to thank them from the bottom of my heart, as their support of the channel is priceless to me and enables me to provide you with videos hopefully on time and with a certain quality I try to achieve, and for that I am forever thankful. In the end, I hope that you enjoyed the video and you found it beneficial. If you have enjoyed the video, then please consider liking, sharing, subscribing, commenting, and so on, especially subscribing because it helps increase the reach of my channel. As per usual, this is the Civil Engineering Essentials channel, and we'll catch you in the next video. Bye bye.